Hi and welcome. Today I'm going to continue my series on material modeling of different polymer materials. The focus today is on a material called CPVC, chlorinated PVC. It's a common material used in pipes for residential and industrial buildings, for example. It's used in those applications because it can take higher temperatures and is cheaper than copper pipes. So today I will talk about what material models work for this type of materials and what can we learn from this. So here's the experimental data that I have. It's uniaxial tension and two different strain rates, both loading and unloading, and there are multiple repeats of that. So it goes up to large strains, and it contains some interesting information about this material. If I wanted to calibrate a compressive response, I probably would do some uniaxial compression testing as well. With this data alone, I can't distinguish the yield stress and tension in compression, but it's still a good data set for example here. So what I will do is what I typically do, I will go through different material models, try to calibrate them to this data set, and I will start with the worst and get gradually to better and better material models. So let's get started. The first material model I will talk about is the Bergstrom-Boyce model. So if I just run this once, you can see that this is the prediction from this material model. And I'm using the M calibration software from Polymer FEM, our company, to do this investigation. It's an excellent tool for trying to evaluate different material models. And the solid lines are the experimental data that I just talked about. The dashed lines are the predictions from this Bergstrom-Boyce model. This specifically happened to be the ANSYS implementation of it, but it's pretty much the same in other finite element solvers like LS-DYNA or Abacus, for example. So this is the Bergstrom-Boyce model. It's developed for rubber-like materials, so it's no surprise that it doesn't work so well. The average error is 22.4%. So that's the difference between the experimental data and the model predictions on average in this case. But we can see that there's a really not so good predictions during unloading in this case. So I wouldn't particularly recommend the Bergstrom-Boyce model in this case. Let's try another one. Another material model that's surprisingly bad in this case is the Abacus PRF model, Parallel Rheological Framework model. So this is a three-network representation that I use yaw hyperelastic elements and power flow elements in these networks. This is my favorite combination of components for the PRF model for thermoplastic materials. It usually works reasonably well. In this case, the error is not very good at all. It's 15.9%. And what I did here, which is what I talked about in one of my recent videos, is that I made sure that this PRF model had the right Poisson's ratio that I wanted to have, but also the correct Young's modulus. In a case like this, where we have experimental data both loading and unloading, and the unloading slope tend to be lower, less stiff that is, than the loading slope, sometimes the calibrations tend to prioritize the unloading and sacrifice the initial linear elastic response. And that is not a good idea, as I talked about in my previous video, because that can give you a poor prediction of very small strains, and that could be not so good in general to have. So here, I made sure that the initial modulus was correct, and that's why the overall fit is really not good at all. It overestimates the permanent set, for example, tremendously. So here is an example of a thermoplastic material where the PRF model is not a good choice. It's not something I would recommend in this case. Let's try something that's slightly better. And this is a super basic plasticity model. This is probably the most basic plasticity model you can come up with. It's isotropic hardening plasticity. It's available in all finite element solvers. It's piecewise linear fit to the data, basically. And you can add strain rate dependence to this in most finite element codes. Adding strain rate dependence or creep doesn't really make much difference here. This looks pretty good and monotonically, but it doesn't do the unloading at all. It's kind of the same problem for a lot of models that I will show here initially. They don't really do a good job for CPVC. The unloading response is linear elastic. The actual data is very different. Not something I would particularly recommend because of that. Another model that's slightly better is this combined hardening model. So it's a kinematic hardening idea analysis. I think this is called the Chabosh model. And it has a little bit better slope to it. If I run this once, we'll see the error is 13.9%, which generally speaking is not so bad. But I don't like models when we can look at the screen in M calibration. We'll see that clearly the unloading predictions are not good. Again, the dashed lines, the predictions here are very different than the solid lines during unloading. You know, that makes me uneasy. I mean, maybe you can say that this is good enough, but we can do certainly better than this, as I will show. So I would try to avoid this type of model. This is the kinematic hardening type model, just because of that reason. Let's try another one. This is what I mentioned a second ago. This is a plasticity model with rate dependence. It improves the predictions just a tiny bit, but not very much. The error is about 12–13% now. It gets a little bit difference between the two different rates here, but it's not working. It doesn't solve the main problem with this type of model. I wouldn't pursue this because of that. And the best plasticity model in this case ended up being the Johnson-Cook version of it. So the Johnson-Cook version has a pretty simple way to represent strain rate dependence, and it has a closed form equation for the plasticity evolution in the material. So the dashed lines here look slightly better. The error is 12.5%. So yeah, maybe you could say this is all right, but again, it doesn't look very good during unloading. It's not making me particularly happy. We can do better, but this is, as you notice, better than some of the traditional viscoplastic material models, like the Abacus PRF model. Kind of interesting, isn't it? Let's take a look at the model number second place position here. So this is the TNV model from the PolyU model library. And this is the one that I have seen to be often the best choice for thermoplastic materials, the most accurate choice for thermoplastic materials. In this case, it came in second of all the models that I tried. The average error is 4.8%, substantially better than anything else. Everything else had more than 10–12% error. We're down now to 4–5% error, which is usually really nice. The way this works is that it captures the rate effects, the softening, and the unloading pretty well. It overestimates a little bit of the permanent set in this case, but it's a pretty decent representation of the experimental data. And this is something that I would be okay using. It looks pretty good to me. I should point out one thing about this model compared to the winner model. In this model, the softening that occurs during unloading here is caused by, it represented using sort of a damage approach. That is, the modulus is reduced during unloading due to the introduction of plastic strain, and that's captured by some of the parameters in the model, particularly the CEPS parameter, for example. So there are things in here that allows us to get this prediction that were designed for this particular purpose, and that's why this works better than the other models. In this case, the best model, the winner in this pack, is the PolyUMod 3-network model. The 3-network model does this with an error of 3.5%. It looks really good everywhere. It captures the softening, the unloading, and permanent set better than anything else. So this is the model that I would recommend. It's easy to use, and it's available in all finite element codes as part of our PolyUMod library. And the one feature here that is really useful and why this model sort of was the most accurate in this case is simply because that this particular model has an evolution of the shear modulus in one of the networks. The mu b parameters goes from 700 to 300 with plastic strain, and that allows us to better capture the unloading response. And that's something that most material models don't allow you to do. This is a unique feature of the 3-network model that is really useful in this particular case. So let's summarize. So here's a summary. On the y-axis, we have the average error in percent. On the x-axis, some of the different models that I looked at. It's really interesting that there are basically two groups of materials. We have a combination of plasticity and viscoplasticity. They don't capture the unloading response very well at all, and that's why I call them bad. For monotonic loading, yeah, we can handle it pretty well, but once you're looking at the unloading or permanent set, and recovery after a load is removed, those types of models here on the left are not good. They're not that accurate. And then we have the material models, the particular TNV and the TN model from the PolyU model library are much more accurate overall for this particular material. So those are the ones I would recommend for CPVC. If you have any questions on this, you can ask them below.